Welcome around the world to this webinar of the International Solar Alliance Expert Training Course. This is David Jacobs speaking here from Berlin. I'm very pleased to be with you again today. Today we have session 31, which deals with sector coupling. So in other words, using solar PV for heating and cooling or in the transport sector. As you probably already know, this is a webinar series organized by the International Solar Alliance in cooperation with the Clean Energy Solution Center. Thank you very much for providing this important platform for solar PV experts around the world. I am Dr. David Jacobs, founder of the consulting firm IET International Energy Transition. I've been working in renewable energy policy design for the last 14 years. And in the last couple of years, we saw more and more countries around the world being interested in how to also electrify the other sectors, the heating and cooling sector and the transport sector, based on renewable energy technologies such as solar PV. So I'm very glad to give a short overview today about the potential solutions. This is a training course consisting of a total of 8 modules, including policies for distributed solar PV, policies for large-scale solar PV. We also have an interesting module 3 on future policies for solar PV, technical integration, market integration, socioeconomic aspects of grid solar, and also a few webinars on solar heating and cooling. This webinar is part of module 5, dealing with system and market integration. And if you haven't watched it yet, please also check out webinar number 27, which is dealing with an introduction to system and market integration of renewable energies. Also, the other webinars of this module are, of course, interesting for you, especially webinar number 30, which deals with solar PV and the role of storage. And since we're dealing with electric vehicles today, which is a type of storage, this might be a very good introduction for you. And of course, module 8, which is dealing with solar heating and cooling, and which also takes a look at some of the solar thermal heating and cooling options, is probably a good addition to this one, because in this webinar today we will focus primarily on solar PV and the potential of using electricity in the various sectors. So here a quick overview of what we will discuss in the next 45 minutes. We will have a short introduction with the learning objective for today's webinar. We want to understand the opportunities and challenges of using solar PV and other renewable energy technologies in other sectors than the electricity sector. And as always, you will get quite a bit of further reading in case you're interested, in case you continue to be interested in the subject after this webinar. And there will be some knowledge checks at the very end, some simple multiple choice questions. So let's start with a learning objective. So what do we want to understand? We want to understand the role of sector coupling in a decarbonized energy sector, because this is a very important introduction to the topic, to understand a certain degree of urgency that we have to also decarbonize the other sectors, which are a little bit harder to tackle than the electricity sector. We also want to understand the basic framework conditions for successful sector coupling. So what kind of infrastructure planning do you need? What kind of market design and rate design in the electricity sector? Do I have harmonized taxations and other parameters within the energy sector? So that's going to take a big part of our discussion today. And of course, we also want to see a few examples of how to use solar PV in the transport sector, and then also how to use solar PV in the heating and cooling sector. So let's start by looking at the challenge of decarbonizing the energy sector in the next couple of decades, and the role that electrifying the transport and heating and cooling sector will likely play. First of all, we probably all know this by now. We are under a certain pressure. There's a certain sense of urgency right now amongst people and policymakers around the world that we actually have to make advances quite rapidly in decarbonizing our energy sector and our industries as a whole in order to remain well below 1.5 degrees additional temperature compared to pre-industrial levels. We don't have a lot of time left, actually. When you look at this graph from Carbon Brief, you can see that we only have about 6 years left. 6 years left to really reduce our emissions. And that would give us a 66% chance of staying below this targeted 1.5 degree objective. If it's 10 years, then we have a 50% chance, or if it's 17 years, it's only just a 33% chance. So the chances that we go above 1.5 degree and more towards 2 or 3 degree, which is a likely trajectory that we're facing under current policies that have been promised as part of the Paris Agreement. It is probably going to enter into more disruptive, more catastrophic climate change. So this is just to underlie really the urgency. And what does this actually mean? Here's an interesting graph developed by the Wuppertal Institute, which kind of compares the remaining coal, oil, and gas reserves that we have left unburned up to now, and how little of this we can actually only burn in the next decades in order to remain well below 3 degrees, 2 degrees, and of course even less if we want to remain below 1.5 degrees Celsius temperature increase compared to industrial levels. So this means, of course, also that in the heating and cooling sector and in the transport sector, we have to move away from fossil fuels as fast as possible and look towards more sustainable solutions, such as electricity from renewable energy sources like solar PV. And as I mentioned in the introduction, we don't have a lot time left. There's really a sense of urgency now. If we act now, and if we peak emissions in the next years, then we still have a 20-25 year period to really reduce emissions to zero. However, if we wait another 5-10 years, then the delay in peaking our emissions will be too late, and there will be too little time to really transform the economy as a whole in order to remain below the targets that we have set in the Paris Agreement. As you probably also know, global fossil fuel emissions are still rising, so apparently we are still nowhere near peaking emissions. Again, in 2018, they were rising, primarily driven by 4 major pollutants. So there's still a lot of work that needs to be done. Now, when we look at the role of sector coupling and electrifying the heating and cooling and also the transport sector with renewable energies, this is actually quite an interesting graph and an interesting study that IRENA, the International Renewable Energy Agency, had produced early this year in the report Energy Transformation, which has been updated in 2019. So you can see here, if you compare the total final energy consumption in 2016, and then you look at where we actually need to get in 2050 if we want to remain well below 2 degrees Celsius temperature increase, then we actually have to increase the share of electricity as an energy carrier in total final energy consumption significantly, from about 19% today to about 49% or 50% in 2050. And of course, you can also see that the other shares oil, natural gas, and coal will be reduced equally rapidly. Some people still argue that maybe the assumptions that Irina is making here are a little bit overly optimistic concerning modern biomasses, which are increasing in this scenario from 5% to 16%. If you're skeptical about this, then you would probably come to a situation where electricity and sector coupling will play an even bigger role, because you wouldn't be able to use that much biomass, for instance, for the transport sector, for the aviation sector, and for trucks and so on. So, but this is an interesting indication of where we actually need to go within the next couple of decades if we want to decarbonize all energy sectors. And now they have broken it down even further, and they were looking at what does this actually mean in terms of deploying more solar PV, deploying more wind energy, and also what does it mean for sector coupling. So as you can see here in the second graph, you see that the share of renewable energies and power generation will have to increase quite significantly from 25% today on a global level to about 86%, even 90% until 2050. And we have made quite a lot of progress within the last years with deploying more and more renewables. However, in the last couple of years, we also saw that total funding for renewable energy investment, total investment in renewables has actually, well, stagnated in the last 3 or 4 years. When you look at the reports on global investment in renewables, you saw that the number of investment was actually more or less the same in 2015, 16, 17, and 18. However, IRENA, in this scenario that they've calculated, is suggesting that we actually need to increase the deployment of solar PV, the annual deployment of solar PV and also wind energy by a factor of 6. So if in 2017-18 we had an annual solar PV deployment of 109 gigawatts, then this would actually need to increase to 300 gigawatts already by 2030, and then increasing even further per year with 360 gigawatts in 2050. And this is, of course, an enormous challenge, not only for the solar PV industry, but for policymakers and all countries around the world together. Now, what does it mean for the other sectors? Where do we need to go? What kind of targets do we need to establish? So when you look at, for instance, passenger electric cars on the road, we saw that in 2017-18, we only had about 6 million cars on the road. However, by 2030, we already need to get to close to 160 million, then up to 750 million and more than 1,150 million in 2050. So a huge increase is needed on this end. And an even larger increase is needed within the heating and cooling sector. So heat pumps, for instance, will need to increase from about 20 million that we saw overall installed in 2017-18. And this will have to go up to 334 million in the year 2050. So also a huge increase that is required. And the same for hydrogen, where as this technology is not yet making any significant contribution to the electricity and also heating, cooling, and transport sector by now. But if we want to decarbonize industries and also the more difficult to be targeted parts of the transport sector, then also hydrogen production based on renewable electricity has to increase significantly. So here again, what this would mean, we see here that electrification of the heat and transport sector with renewables will account for about 36% of emission reductions by 2050, and then renewable energy deployment in the electricity sector will then account for the remaining 39%. So both of them together under this IRENA scenario will actually deliver 75% of required emission reductions within the energy sector. This is not just IRENA, which came up with these types of studies at a national level. We also had a recent study looking at what full-scale decarbonization of all sectors actually means for the European Union. And this is now a comparison of the primary energy demand in a fully decarbonized energy system, comparing today and what we would need to have until 2050. So you can see here very dramatically again that fossil fuels will have to reduce very considerably, and then electricity from renewable energies will have to increase very dramatically at the same time. So just to show you that this is a tendency that we see for all energy markets that are planning full decarbonization by 2040, 2050. So that was just a quick introduction into why we actually need sector coupling, and that we would actually need it pretty fast if we want to comply with the targets laid out within the Paris Agreement. So let's now look at some basic parameters that are needed for making sector coupling effective. And here's an interesting graph, which I use in a lot of my presentation, which has been produced by the International Energy Agency, which kind of shows you the complexity of the future energy system and also of the future electricity system, where balancing supply and demand at the distribution level will already play a much more important role. We need more storage. We will have the electrification of the transport sector. We'll probably also use more centralized power generation for heat generation. We have more and more renewable energy deployment, and all of this, of course, has to be embedded in a smarter and digitalized energy and electricity infrastructure. So looking at sector coupling, it of course means using electricity generation via certain ways into the power to mobility sector, so using it in the transport sector, also maybe power to gas for some parts of the transport sector. And as already mentioned before, it also means using renewable electricity for heating and hopefully also cooling. So this is kind of an outline of what we will discuss in the next 30 minutes. So first of all, the framework conditions for successful sector coupling, and then a few case studies on solar PV and electric vehicles and solar PV uses for heating and cooling. So the framework conditions. You will have to start by looking at how the different energy sectors within your jurisdictions are actually treated. Are they all treated the same? Are there substantial differences within the treatment of these sectors? Do you maybe have subsidies for some sectors and not for others? Do you maybe have subsidies for using fossil fuels within the transport sector? However, then you have other surcharges and levies that you put on your electricity sector. So in the end, the objective should be that you come up with a more harmonized system of taxation, subsidies, and levies for the different sectors. That means for electricity, heating, cooling, and transport. Because if you fail to do so, and if you have additional burdens or lack of subsidies within the electricity sector, then of course it becomes less attractive using electricity within the other sectors, because you're putting a burden on electricity which their competitors within the heating and cooling sector or within the transport sectors don't have. And a very simple example, for instance, is taxation on fuels within aviation. In many countries, I would probably think in almost all countries, fuels for the aviation sector are very little taxed because of international competition as well. However, if you then compare this, for instance, with levies that you have on your electricity, or even levies that you have on other parts of the transport sector, you will probably see that there's an imbalance, and therefore you won't have any incentives of electrifying this part of the transport sector anytime soon. And of course, it is also very important to reduce the remaining subsidies. And this is, well, recommended by all major studies that are dealing with how to manage the transition towards more sustainable energy sectors. A major part of it is, of course, reducing any subsidies that is still existing for fossil fuels within your country. So this is the first step, and this is, of course, it is quite simple to put this on one slide. However, to implement it in political realities might take quite a long time, because, of course, if people are used to having subsidies in certain sectors, then they have adopted their behavior to this, and then changing this behavior by reducing subsidies or increasing carbon taxes or whatever it is, might, of course, confront policymakers with quite a lot of opposition from the public, and therefore confronting this might also take some time. However, as we have learned from the beginning, we don't have a lot of time left, and therefore these issues need to be tackled as soon as possible. Then another very important aspect of successful sector coupling is, of course, long-term infrastructure planning. And we are talking here primarily about the planning of the electricity system and the gas infrastructure. In the electricity infrastructure, we are, of course, talking about grid expansions. We're talking about the digitalization of the energy system, also establishing better charging infrastructure for electric vehicles, and so on and so on. In the gas infrastructure, we are starting to discuss in quite a lot of countries of how to adopt the existing gas network in order to also allow green gases to be fed into the system, so that renewable electricity, which is then converted into green gases, methane or others, can actually be fed into the gas network and then used maybe in different times and different locations in order to make use of it in the different sectors. And last but not least, what is also emerging in quite a few countries is better interconnections, better interlinkages between electricity and gas infrastructure planning. So when you look at your electricity expansion plan, for instance, for the next 10, 20 years, then it definitely makes sense to already combine this with your gas infrastructure planning, because if we're talking about sector coupling, if we're talking about providing more green gases from the electricity sector to the gas infrastructure, then of course it makes a lot of sense to combine these frequently separated planning processes for the electricity sector and the gas infrastructure. Now, going back at the market design of the electricity sector again, what is really crucial for any success in sector coupling is, of course, rate design. So how do I structure my electricity bills in order to incentivize a certain behavior from customers? And luckily, we already had 2 sessions on rate design in this webinar series. It was number 8 and number 9, if I'm not mistaken, on rate design and advanced rate design. So here just a quick summary. Please also check out the 2-hour webinar on this. You have traditional rate design, where you have volumetric charges, fixed charges, and demand charges, which can be implemented without any advanced metering infrastructure within the existing metering infrastructure. However, in order to make electricity systems smarter and in order to confront your final consumer with the price signals that actually reflect the supply and demand curves within the wholesale electricity market, then you have to move to smarter rate design. And this includes time of use rates, critical peak pricing, real-time pricing, and locational pricing. And of course, To implement those, you also need to roll out smart meters within your jurisdiction, within your country, and then ask utilities to offer these rates, these types of rates, also to customers. Here, just a quick summary again of how these look like. So time of use rates at the very top graphical illustration. You can see here, for instance, a very simple time of use rate, which kind of depicts the two peaks that you have within a certain jurisdiction. So during this peak demand periods, where you have more demand and probably not more supply, there's more scarcity within the market and prices will go up for producing electricity, and therefore also your prices for your final customers should go up in these hours in order to give them an incentive to consume less electricity during those peak demand hours and then more electricity during off-peak hours. Another options for rate design is critical peak pricing, where you, for instance, say, well, we have a few hours within a month or within a year where we have very high electricity demand within our country, and meeting this electricity demand really costs our utility a lot, and they have to run each and every power plant, which sometimes are very expensive. And therefore, for those hours, which can be rather well anticipated based on historic data, then you can say during these peak hours, we will introduce some critical peak pricing. For instance, that the electricity price all of a sudden gets 5-6 times higher than it normally is. And that gives a very clear price signal to everyone who is then participating or who is part of this rate design option to really reduce power demand during those hours. And this can actually help to stabilize the electricity grid, first of all, and also to make meeting peak electricity demand during those hours cheaper and easier for the utility. Peak time rebates is the same, but not with a stick, but with a carrot. So instead of penalizing them, you actually pay them money for reducing the load. And last but not least, we're talking about real-time pricing, hourly markets, where you're really trying to pass on the price signal that you see on the wholesale market all the way to your residential, commercial, and industrial customers. And this is, of course, the most effective way of incentivizing certain behaviors of your electricity consumers within the market framework. And of course, also a few words still about self-consumption of solar PV. This is also one of the important framework conditions. Of course, when you add additional loads to your electricity demand by, for instance, heating your house with electricity or charging your battery of your electric vehicles, then of course this also allows you to increase your self-consumption. We discussed this already in the session on storage, session 30 of this webinar series. So here just a quick repetition of this, that by having additional loads or storage options, you can actually avoid feeding in electricity into the grid, and thus also reducing the need for grid expansion within your distribution network, which might be beneficial for the electricity system as a whole. There's actually an interesting study by Agora Energiewende, which has looked at these options, not only from a household level, but from a more macroeconomic level, comparing power markets where solar PV systems are producing without storage and just feeding in every excess electricity into the system, with, on the right-hand side, an electricity market where solar PV is combined with battery storage and heat pumps within separate households. And what you can clearly see here is that there's no more influx of solar PV into the electricity system during the winter months, because there's of course also huge load required for heating in Europe. However, there's relatively little changes towards the influx of solar PV into the electricity system during the summer month, which is not such a bad problem because we have our peak demand within the winter months, and therefore by having solar PV in the system, the influx can actually be avoided during those months. Now let's look at some of the power to mobility options that we have with solar PV. Here just a quick summary again of what we've discussed in session 30, where we talked about solar PV and storage. We were looking at the various services that storage can provide to the electricity system. And of course, when we talk about electric vehicles, we're also talking about storage, because an electric vehicle with a battery in the back of the trunk or wherever it is suited in your electric vehicle is of course at the time that it is connected to the electricity system also a storage unit. So a lot of the services that are part of energy storage more generally are then also applicable to electric vehicles. So you can actually do arbitrage, electric energy shifting over times. You can also avoid upgrades to the distribution network if you have intelligent charging applied. You can also use it to reduce your retail electricity price by shifting the time of charging on a household levels. You can avoid demand charges. And as mentioned already before, you can also increase self-consumption. However, we also have to keep in mind that EVs could also cause additional peaks in electricity demand. And this is why we had this introduction again on rate design and of how to incentivize customers to change their electricity consumptions, to change when they are charging their electric vehicles, and to move these charging periods towards off-peak periods. So these price signals are very important and they could work. However, policymakers and experts are also discussing alternatives, because some people say, well, the price signal needs to be so extreme and so high in order to incentivize any change in behavior that this might be politically very difficult to implement. Therefore, there's also some discussions about maybe making the distribution system operator, to putting her in charge of deciding when an electric vehicle is charged or not. So giving them directly control over the charging process to a certain extent, of course. So once you connect your EV in the evening to your power plug at home, then the DSO could have by remote control the options of charging it according to the power system needs. Some people also say, no, that shouldn't be the role of the distribution system operators, but rather the role of aggregators that we see emerging in more and more liberalized electricity markets, that these aggregators simply, well, connect and aggregate thousands of electric vehicles within a given region. And then based on price signals that they receive from the wholesale power market, they can actually coordinate the charging of these thousands of vehicles more easily. And some people also say that we should have load management systems at the distribution level. And for instance, you see here a substation with a transformer and all of the households with electric vehicles behind this transformer. And of course, it will be very important to stabilize supply and demand of electricity at this distribution level as well. And therefore, behind each substation and each transformer, there should be some coordinated charging and discharging, if necessary, of electric vehicle batteries. And therefore, we would need a load management system behind this points. And there has been already quite a lot of research on the potential impacts of charging electric vehicles in accordance with the needs of the electricity system. So instead of traditional charging with timer peak, when everybody comes home, connects the car to the in the garage, and then goes to dinner, and then with a timer, all of the electric vehicles start charging at the same time, and they will put an additional huge burden to the electricity system, additional peak demand. You could actually implement smoother charging, which also coincides hopefully then with peak supply of solar PV electricity, and therefore you could actually not only theoretically but also practically use a lot of the solar PV which is put into electricity systems around the world during noon hours. We discussed this already during the session on storage, but I wanted to repeat this also for the electric vehicle discussion. There is, of course, the risk that by having storage within your electric vehicles, you could make things a lot worse. Here, again, we have a solar PV system which is connected with a battery, and we have a situation where the battery is charged during the morning hours, and then once the battery is fully charged, you see a lot of peak solar being fed into the system with very high steep ramps, which is of course not beneficial to the system. However, as mentioned before, you can use the battery, and in this case, this would be our electric vehicle, to actually smoothen the feed-in of solar PV during peak hours, during noon or 1 or 2 o'clock, whenever it happens in your jurisdiction, and therefore also help to stabilize the electricity grid. There has been already some studies that have also tried to quantify the impact of smarter charging of electric vehicles on electricity systems. For instance, a recent study from Agora Energiewende from 2019, I think it was, where they have looked at the potential impact of smarter charging on the German distribution network, arguing that the cumulative distribution network expansion costs can actually reduce by 33 billion euros until 2030. So that's, of course, a pretty huge number, which once again shows you the potential benefit of smart charging compared to not so smart charging of electric vehicles. This is just a quick introduction on the charging of electric vehicles. Maybe we should also have a quick look at potential other power-to-X technologies. In order to decarbonize the transport sector, you have primarily 3 options. That is, using solar PV or other renewable energy or low carbon technologies directly. You have the options to transform this electricity into liquids or gases. And of course, there's also the options of using biofuels from biomass and biogas directly. However, this is beyond the scope of our topic here because we're focusing on solar PV. Here again, quite an interesting study from IRENA, where they looked at the potential of the transport sector in being decarbonized. And they were then looking at the different technologies that are used for the different parts of the transport sector, arguing that for small cars, urban mobility, we should definitely use direct electric vehicles, whereas for some other parts of the transport sector, like trucks and buses, maybe hydrogen or other gases would be required. And then again, they argue that biofuels should mostly be used for very energy intensive transport, such as shipping and aviation. To put this into perspective, what should you really do? What is the most efficient way of using renewable electricity, of using solar PV for the transport sector? Here again, the Agora Energiewende study, which I've already cited before, which is analyzing the amount of renewable electricity that is needed for various powertrains and fuel combinations if you want to run your vehicle for 100 kilometers. And it's quite interesting to see that if you use the electricity directly within batteries with direct charging, then you would actually only need 15 kilowatt hours to run 100 kilometers. However, already when you move to the hydrogen option, fuel cell vehicles plus hydrogen, you would need more than twice as much electricity. And then if you want to use renewable electricity within combustion engines, this even goes further up. And here's actually the reason why. Here you can see the transformation processes that are required, and of course also the losses that you have during these transformation processes. In the case of battery electric vehicles, you have relatively little losses. You have a few transmission losses as always, and you have a few losses within the battery. However, in total, you still get about 70% of the renewable electricity that you put in out once you use it for the transport sector. However, the share is a lot lower when you look at the options of fuel cell vehicles, and even worse when you look at internal combustion engine vehicles using renewable electricity. So of course, for the electrolysis process for producing hydrogen, you already have quite significant losses. Then compressing it, using it into the transport sector via fuel cell, you have another very significant loss, and then you have additional losses within the electric motor or the mechanics of the motor, so that in the end, only 26%, or in the case of internal combustion engines, only 13% of the total energy that you were producing with solar PV or other renewable energy technologies overall are actually being efficiently used in the transport sector. And this, of course, underlines once again that using solar PV or using renewable electricity is by far the most efficient way by using it in batteries directly. And therefore, there's also some research or some testing now being done of also using it for technologies where some people argue, well, these are hard to be electrified and therefore we need to move to hydrogen altogether. However, here you see an image of a new truck track in Europe where trucks are run on electricity grids. However, we still need hydrogen to a certain extent or other green gases in order to electrify the more difficult to reach sectors of the transport sector. And therefore, you have to, well, accept some of the losses you are making when actually transforming renewable electricity via electrolyzer into the gases that are required, and then using it for heavy duty or trains or ships or the aviation sector. So this was a quick look into the electric vehicle and transport sector. Now just another 10 minutes on power to heat, power to cooling solutions. Actually, buildings use quite a lot of energy that is consumed worldwide. More than 30% of global final energy consumption is used in buildings. Depending on where you live, you might use a lot of electricity or very little electricity for heating. That also depends largely on your climate. We normally see in milder climates, we see more use of electricity for heating and cooling purposes, whereas in countries where it really gets very cold, we don't see it as much. Electricity supplies about 24% of the current energy used in residential and 51% in commercial and public buildings. And the two mostly discussed and implemented options for using renewable electricity within the heating sector are heat pumps for space heating and hot water, which are highly efficient, however, which also require major retrofitting of the buildings, and therefore also quite a lot of high upfront capital that needs to be invested, and the other one is a direct use of electricity for resistance heating in boilers and furnaces, where the electricity is normally used for heating water that is then circulated within heating systems to provide space heating. Here the efficiency is relatively low, but some people argue that in electricity systems where we have a large influx of solar PV and wind energy, the efficiency should no longer be our primary concern, because we might have abundance of electricity that can be used. And we also see that these options are normally used either in well-insulated houses or, as I said before, in milder climates where you don't have such a lot of space heating requirements. Just to put this into perspective, there might of course also be problems with using electricity for heating, and here we come back to the problem that we have discussed right at the start, that actually sector coupling might actually lead to additional peak electricity demand within your system. And therefore I also wanted to mention the case of France, where already in the 1960s, 1970s, electric heating was actually promoted by the government, which was also part of the French nuclear program, where they wanted to create additional demand for electricity. However, we're currently in a situation in France where peak electricity demand during the winter months is actually twice as high as during the summer months. And the single cause for this is actually heat pumps and using electricity in the heating sector in France. And this, of course, creates quite substantial additional cost for the French electricity systems, because meeting peak demand is already quite expensive. And if this peak is twice as high as your usual electricity demand throughout the year, then this has actually quite significant implications for your electricity system. And another problem, especially in countries with cold climates, is of course that during those months when a lot of electricity is needed for heating, you don't have a lot of influx from solar PV, where some people then argue, well, moving our electricity systems towards more renewable energies, including solar PV, will not really solve the problem of having additional load in the systems for electric heating if we really want to go down the sector coupling path. And what is actually happening in France during the winter months is that a lot of electricity is then imported during those months from the neighboring countries. And since also the neighbors like Germany don't have a lot of solar PV in the system, maybe a lot of wind, we also saw quite a lot of days and months in the last couple of years where dirty coal-generated electricity from Germany was exported towards the French electricity system. And this is, of course, not what we want, and therefore we also have to ask in the heating sector whether maybe synthetic fuels are a more viable options, where we could then also produce more solar electricity maybe during the summer months, transforming it into synthetic fuels such as hydrogen or synthetic methane, feeding it into the existing gas infrastructure, and then maybe using it during the winter months. But as already shown before, we also have quite a lot of efficiency losses if we go down this route, and therefore both options need to be compared rigorously. Finally, a few slides on cooling with solar PV, which are actually still emerging technologies. It is quite intuitive that the need for cooling with air conditioning and the influx of solar PV from solar PV systems on your rooftop are quite coincidenting. They're quite occurring at the same time of the day. Here is one example, which is actually showing that the PV output marked here in red is happening a little bit earlier than peak demand of air conditioning. which makes sense because well, before when the sun comes in, it actually gets warmer in the afternoon, and then already the peak supply of solar PV electricity is gone. However, the supply of solar PV and the load profile of air conditionings are actually still matching quite well. So one could think that using solar PV directly in the cooling sector will become major options. And of course, by electrifying or by using more and more renewable energy technologies within the electricity sector and moving towards 100% renewable energy-based power systems will, of course, automatically also increase the use of renewables in the cooling sector. Here's just a few background slides, which are quite interesting. A study done by the International Energy Agency on the future of cooling, just showing you the percentage of households with air conditioning, with the Japan and the United States and Korea leading, where more than 80% of the houses already have air conditionings, but also other countries in warmer climates picking up quite rapidly. And with climate change happening in more and more countries, and many more countries moving towards areas or towards temperatures where it is quite difficult for human beings to work in, we would probably see a very sharp increase of electricity demand related towards cooling. And this is actually reflected in this slide, where you can see that cooling is actually the fastest growing use of energy within buildings, being responsible for about 37% of final electricity demand growth until 2015. So far exceeding the demand growth that we see in the heating sector and the lighting sector, or even in the residential appliances sector. So this really becomes a huge challenge to decarbonize the entire cooling sector within the next decades as well. And what the study also shows from the International Energy Agency is that cooling will actually increase peak demand. But this is just some examples where they have calculated the potential effect of cooling on electricity systems. And you can see that peak demand is increasing by 22 up to 45% in various countries within the reference scenarios. Now, here just a quick look at some of the cooling technologies. As I mentioned before, please also check out the webinars on solar thermal for the right-hand side of it. And then there's, of course, some solar electric cooling technologies, PV plus compression cooling, which is currently being installed in more and more countries around the world. However, there's still quite a lot of R&D going on in this sector, and the technologies are still quite significantly more expensive than traditional air conditioning technologies. So, this being said, let's take a step back and look again at sector coupling as a whole. Quick summary, we hopefully understood now that sector coupling and the increasing electrification of the transport and heating and cooling sector is urgently required for decarbonizing the energy sector as a whole. And in order to make this happen quick and successfully, we first of all need to tackle a number of general framework conditions, namely infrastructure planning and better coordination of the electricity and gas sector. Then harmonizing taxes, levies, subsidies within the different sectors, within the electricity, heating, cooling, and transport sector to create a level playing field between all of those. And then, of course, some major modifications of rate design, making rates smarter, and also rolling out smart metering technologies to allow this to happen. Because the consumer needs to be confronted with the right price signals to really reduce and increase peak electricity demand to a minimum and to really charge the electric vehicle and use electricity for the heating sector, not during peak demand periods. So here, finally, quite an extensive list of further reading of the reports that I have mentioned during the webinar, but also other additional reading, also some more additional reading for rate design that we had discussed already in session 8 and 9 of this webinar series. Thanks again for the International Solar Alliance and the Clean Energy Solution Center for making this happening and for providing this platform for solar PV experts around the world. I'm also very thankful. I'm closing now with a quick point out at some multiple choice questions which will follow this webinar. Thank you very much for listening and hope to hear you again in the next webinar series.